All right, I'm going to actually burn a little bit of my time talking about how much I enjoyed the previous talk, and I'll explain why. I'm a pretty easygoing guy, but I'll give you a secret. There's a way to get me really angry, and that's to whisper. Just come behind me and whisper in my ear. Roadrunner was a success. Was a failure. It was a dumb idea, and Cell they canceled Cell, so it was a bad idea. That'll get me really riled up, and here's why. Because when we were doing that, I was at Los Alamos before going to Oak Ridge. The whole time we said it wasn't about the Cell. This is about the future, where things are going, and all the codes that we modify for Roadrunner are going to be better positioned, and all of that was true. And it gets forgotten, and I hear those kind of negative things all the time. Partly because people don't know the full story that you have to go behind the fence to hear, but partly because it was Cell was canceled, and so that gets kind of muddied up in it. The other thing is I'm going to talk about. So that was a completely different system than the Phi that we just heard about. And we saw exactly the same thing. Those codes ran faster after the modifications for Cell. The same kind of modifications made the CPU codes run better. And I'm going to show. I may not highlight it well enough, so I wanted to say it first. We see the same thing on the GPU on the codes for Titan. All the ones that we've modified run about 2 times. Just the CPU only codes run faster. So all that stuff that you hear about reworking codes for these architectures is a good idea, regardless of the underlying architecture. It remains true. So that was one of the best analyses that I've seen. We never did a publication that I saw that really delved into how much better the CPU versions were after the Roadrunner work, but that was a nice talk. So anyway, I burned a couple of minutes, but I think it was worth it. So anyway, okay. So I'm at Oak Ridge. If you saw the early versions of the agenda, my colleague Doug Cothey was supposed to give this talk, and originally I thought that I would change the title, which was Experiences Using Accelerators at ORNL. I left it a little too late to do that, and so I left the title the same and managed to kind of work what I wanted to say into that title. So we'll see how that goes. I did add a subtitle, which was Application Readiness, which is preparing the codes for Titan, the early science, and then I'm going to try to wedge in there some industry impact. So we'll see how that goes. So I'll talk a little bit. Most people probably know about the DOE Leadership Computing Program. I'll talk about Titan, which is the leadership computing machine at Oak Ridge, the preparation of codes for Titan, and then I'll veer a little bit toward the CASL, which is a consortium for advanced simulation of light water reactors. Some of the people here are probably getting sick of me talking about that, and it turns out that I stood here 4 years ago at the 2010 meeting and gave a longer presentation all about that, and that was when I was all excited about how it was going to be unicorns and things related to that. And I checked, and that presentation is in the archives of the old meeting, so if you want to see more about that, dig that up. So I'll just talk a little bit about what we've done in those 4 years since then. And how that's connected to the application readiness work and the early science, because one of the codes was part of that program. And that's how we've impacted industry. So the DOE Leadership Computing Program, there are 2 facilities, one at Argonne and one at Oak Ridge. These are 2 large machines that you're probably very familiar with. One's Blue Gene, and one's the Cray with GPU accelerators. And there are a couple of ways to get access to those machines. The 2 biggest ones are the Insight program, run out of the Oscar office, Advanced Scientific Computing Research Department of Office of Science. And then they have another, oops, that's the wrong way. Is there a, yeah, there you go. ALCC program, which also allocates time on these machines. And then there's a chunk that's discretionary that's handed out for individual PIs and for industry collaborations and things like that. But the largest chunk is the Insight program. And it's interesting to note that the request for time through this program, this is for both the Argonne and the Oak Ridge, the overall program. The number of projects has remained roughly flat, but the demand for cycles has gone up quite dramatically over the last few years. I don't have the 14 numbers on there. This is the picture of Titan that you're probably very well aware of by this time. The most important point, of course, is that most of the processing power is in the GPUs. If you don't use them, you're throwing away about 90% of the machine. Yeah, we try not to talk about LINPACK anymore, but everybody does anyway, until we get the HPCG or something like that as a more accepted standard. We do have some codes that are performing very, very well other than LINPACK. Let's see. So I think you're mostly pretty familiar with that machine by now. So when this machine was on its way, we set up what we call the Consortium for Advanced Accelerated Application Readiness, and it picked a few representative applications to extract kernels from and prepare for the GPUs. So we worked with the teams. We assigned people and ported to CUDA or whatever programming model the team wanted to use. So these were 6 different applications from across science domains that represented the kind of workload that Titan has, and tried to represent different algorithmic motifs as well. This is a set of those 6 applications, and I'm going to show. So you've got combustion, astrophysics, radiation transport, astrophysics, Denovo, which is the one that does neutronics or neutron transport in reactors, which I'll talk about, and also shielding calculations, a climate code, molecular dynamics. So really spanned a good range of science applications. So the plan was to assign for each app, give an OLCF person, a Cray engineer, an NVIDIA developer, and then so give them a significant amount of help to prepare their applications. And we had to define a problem that was relevant that each application would run, and then devise a plan and make the modifications. So the goal was both to try to get the best performance out of that application, but also, as one of the questions indicated, try to identify aspects of that acceleration path that would be helpful for the broader community and for other applications. So this is a summary of a few of the 4 of the applications, how they performed on Titan versus the Jaguar, the XE6. So these were fairly early results, and some of these have gotten better since then. But you see, LAMPS was actually a mixed precision, so it gets a little better performance. So it's over 7. And the other applications are more in the 2 to 4x range. We did an interesting thing with WL-LSMS and looked at the power trace, compared the power over an entire run with and without the CPU. So you're not only concerned about the speed up, but also what's the total power that you're using. And so that was kind of an interesting result to see that it was, runtime is about 8.5 times faster. But the energy consumed is also significant, over seven times less for the accelerated code. So that's kind of nice to know. And we're doing this for some of the other codes now. In particular, Denovo, which is the one that's relevant to my work in CASL. We took the sweep portion of that code out, which is kind of a wavefront algorithm, sped that up using CUDA, and now we're doing some real problems with it. And that's the results on the right are quite new as of, I don't know, last night. And so we're doing some larger problems with that and looking at the time, and we're doing a power trace now as well to see what that looks like for this code. So as you see below, the kernel was rewritten in C++ and CUDA, and this is the part I wanted to point out, that the refactored code was twice as fast on Jaguar with the CPU only. So that's the point I was going to touch on, that the previous talk made very, very nicely. And also another important point is that this, unlike some efforts like this, it was done very tightly integrated with the regular development team, and so the CUDA code is actually part of the mainline code, and it wasn't like a one-off effort. It's actually in the mainline code as part of the normal suite. And this code scales very well to well over 200,000 cores, and so it performs very well. This is we're trying to track how the codes are using the GPUs, and we don't have. I think there's some new methods to do this better. This is a kind of a crude and primitive way, but we wanted to try to track. Are the application codes starting to use the GPUs? And so this is only measuring is a code that's running linked against the CUDA library. So obviously, you could link against them and not use them at all, but people generally don't do that. But still, this doesn't give you a good feel for how effectively the codes are using the GPUs. But we're trying to get a little better handle on that. And you can see it going up. I don't know what the cause of this dip here is. I'm not sure what's going on there. If we were just running some other things or what. But overall, it looks like the codes are tending to use the GPU a little bit more. Okay, so I'm going to switch gears and talk about CASL just for a second. We've talked about this before, and so you're probably getting tired of it. But it was so Secretary Chu back in 2009 proposed these energy innovation hubs spread across DOE. One of them was devoted to modeling and simulation for nuclear energy. It was the only one of the hubs that was specifically modeling and simulation. So that's the other ones would be about solar or building efficiency or something like that, and they could have a simulation component. But this was the only one that had modeling and simulation in the title and in the mission, and so that was very exciting for us to go after. And so the goal was to bring high-performance computing to the nuclear industry, which was very familiar and was very much using simulation, but hadn't really come to the HPC. Back in the 70s, they were part of the HPC community, but they had kind of fallen off from that. So advanced numerical methods, increased coupling of the physics, and improved models, and so we put together a very large team, 10 institutions, which you see over here, multiple national labs, multiple universities, and really significantly 3 industry partners: Westinghouse, TVA, and the Electric Power Research Institute, EPRI. So this has been a unique project, and it's probably the closest I've ever worked in my career at DOE with industry, having our work kind of not directed, but guided by what's relevant to industry problems. So that's been a very exciting experience. So an important component of what we proposed in the original proposal was the concept of test stands. And I'm not sure where that term came from, but what it meant was, as our tools matured, we would push them out to one of the industry partners as sort of a beta test for going broader. And they would use it with our help, but as independently as possible. They would use our codes for some other problem that we hadn't used the tools for before. So we set up a process for doing this, and the first, we set up that Westinghouse would be the first test stand, and then we'd do EPRI and then TVA. And so at this point, I think when the slide was made, we'd only done Westinghouse. At this point, we've also done EPRI and TVA. The TVA test stand is in process. And they all did different things. They took different parts of the tool set that we were developing. Westinghouse was focused on neutronics, which I'll talk about in a minute. EPRI was more focused on the fuel behavior, and TVA is more interested in CFD. So they're using they're doing a purely flow problem. So it's been extremely valuable because it pushed us to have better code installation processes, look at our input processing for the machines, and just gave us a lot of feedback on use of the codes and applicability, and pushed us quite a bit. So what Westinghouse did was they took it and deployed it on an in-house cluster. So they don't have Titan, but they have their own machines, which are quite a bit smaller, but they could still do relevant problems. So they took it, put it on their own machines, and they used it to analyze the AP1000, which is a new reactor that they're building. There are a few planned for here, but a bunch of them in process in China right now. And one of the exciting things is they were able to use it to kind of compare to their own tools. So it wasn't used to do safety calculations or anything like that. So these tools are a little new, so they're basically using them in a confirmatory manner to compare against the tools they already use, see how they work and how they compare with answers and efficiency and speed. And so that's been an interesting process. The AP1000 itself is a very complicated core. It's one of the most difficult, and so a lot of the approximations that have been used in the past really start to fall down. And so it's very helpful to have the advanced tools that we've developed in CASL to analyze a core like this. It's very heterogeneous. There are partial length rods that burn away with time. There are coatings on some of the rods. All of this in an attempt to get a flatter and more consistent power distribution, because that raises the efficiency of the reactor. So it's a very difficult core. It's a great example of one to try to analyze with the tools, and so you can see some of the differences and advantages of the advanced methods. So in early 2013 is when we started the test stand discussion with Westinghouse. They proposed a problem. We deployed it in June of 2013. They did their analysis last year, and then January of this year, they completed their analysis and documented it. Now that was using one method of neutronics that would run on their cluster. So now I'm going to tie this back to the early science program. So that was not using Denovo, not using also Monte Carlo, which is even more computationally expensive. But since then, as part of the early science program with Titan, so this gives you a table of there are multiple ways of approximating and solving the Boltzmann transport equation, which is what all these things do to try to predict the behavior of the neutrons in the core. So you've got everything from simplified PN, which is basically slightly better than diffusion method, and you end up solving a big linear system. You have discrete ordinates, which is basically a Cartesian mesh and a wavefront algorithm. You got method of characteristics, which is which handles complex geometries very well, complex but regular geometries very well, and it's kind of like ray tracking. I don't want to say ray tracing because it's a little different than that. And then Monte Carlo, which is a full particle method where you operate on the CAD, basically the CAD geometry. You can do continuous energy. You don't have to make many approximations at all. So what we did was, so Denovo, oops, dang it, I did it again. this is the code that was a part of the Titan application readiness and early science program. And this is the method that was used for the test stand. And then this is a new method, the Monte Carlo, which is extremely exact, extremely accurate, and scales very well and gives excellent numbers. But it requires a machine like Titan. Westinghouse wouldn't be able to run that on their machine. So what we did as part of the early science program was compare this method, run the same problem, the AP1000 problem, using this method and the early science code, and then shift the Monte Carlo code. And we compared these all to a very well accepted. This Kino code has been around for several decades, and it's another Monte Carlo code. It's venerable. It's been used for many things, but it doesn't scale very well. It's not a modern code. The answers are accepted as very good, but it's not something to ride into the future, whereas Shift is. So we did this, compared those, and compared accuracy and run times and efficiencies for all these three different codes, and in the process ran what I think are probably some of the largest Monte Carlo runs ever, 1 to 2 trillion particles to analyze this core. And got some very nice results. Westinghouse is really thrilled with the results they got, and doing a lot of analysis. And so I wanted to say thanks to IDC, one of the Westinghouse guys that did most of the work here, Fausto Francischini, submitted for the IDC HPC Innovation Award and won that in the last round in June, I think it was, or something. So he's very, very happy with that. We're all very happy about that. And this was very important to Westinghouse, I wanted to say. They're really happy about this. So we got excellent agreement with Kino 4, which was the older code. We ran up to the full machine of Titan, and we've been doing these extremely fine mesh SN calculations using the early science code Denovo. This is underway. Well, we're almost done with it now, and they look very good. But it is much more expensive than the low order method. But running these multiple methods gives us a great confidence in the answers, and gives us a real way to compare the answers we're getting. So in closing, I think I wanted to say that we are preparing some of the other codes that we're using in CASL for the accelerators. They're not quite as far along as Denovo is, but our CFD code, Hydra-TH, which is out of Los Alamos, we're working with NVIDIA to use their AMGX library and get that in to use to make use of the accelerators. Impact is the other neutronics code that I didn't talk about. It was a little premature to have that as part of the suite we were compared to, but it's very promising. And so we're looking at accelerating that. It's all in Fortran, so we're looking at OpenACC for that. That'll be the most appropriate path forward there. And finally, that Monte Carlo code Shift, we're very interested in accelerating that as well. So we've identified some NVIDIA staff to help with that. And so we've actually made a mini app, which is, that puts together in a non-export control form the key algorithms from both Denovo and from Shift, and the SPN as well. Which makes it much easier to hand off to, that'll be open source to, as soon as we get the final export control ruling, which we're waiting on, we're going to put that on GitHub, and then anybody can take it and try to help us, make it run faster. I think that's my last slide, so I hope that hits some things of interest.
So, do we have any questions?
Just one. You stressed that the optimization work for the GPUs also benefited performance on the CPU. What about in energy efficiency? Does that imply that the codes ran with better energy efficiency on the CPU afterwards?
Only I haven't seen the traces, but only in that they ran faster. So it, just whatever the reduction in runtime would be by that factor. That's interesting though. I don't know if there would be anything more than that.
Any other questions?
Watch the edge. Watch the edge.
Yes.
John, what has been the industrial receptivity to using the GPUs? Or are they just coming along because they're part of CASL and it's I don't know, it's becoming more second nature because it's been inculcated right from the beginning?
I think they're skeptical. They're sort of still in that denial period. This isn't really going to happen. Something's going to save us from having to do anything special. And they're probably getting tired of me telling them that they better think about it. But I would say they're a little skeptical. They're very conservative, very, very conservative. Yeah.
I'm going to ask the same dumb question I asked the last presenter. Are these the optimizations you did and the rewriting you did something that feels like a bag of tricks you want to code, or things that are unique to this code?
The question was whether the optimizations are broadly applicable, and I think we try to do them in a way that they're broadly applicable. But obviously, if they're some of them are very code specific. But one reason we wanted to make a mini app so that you could work in that, you could see, so you could take see how the wavefront algorithm is accelerated here. And if you had another wavefront, ish algorithm, you could use it for your code. I think the particle, when we accelerate the particle stuff, that's going to be pretty broadly applicable. So we try to do that. And solver libraries obviously are more portable. But it's tough to balance that when you're in a kind of a milestone-driven program where you're kind of driven to get your goals done, and so kind of the broad applicability is a little less of a goal. We try to do it, but it doesn't always. It is sometimes more code specific than we'd like.
And if I could follow up, the changes that you made sounded like they affected the physics enough to make you get worried about fidelity, or was it more you're just being conservative?
No, it's more that we have a basket of methods, and some are so expensive you have to run on a big machine. But we like to have those and do those runs so that we know in the faster running, more approximate methods, what is our error, what is our uncertainty at those for the more approximate methods. So it's more due to that than the code changes don't change the answers.
Okay, thank you, John.